This week we have again 5 problems. I think the first couple are again warm up, and then the last 3 are more string type of problems. So let's get to it. Okay, the first one, again, I'm assuming that you have read the problem. It's an encryption scheme where letters, uppercase A to Z, are converted to 0 to 25 and then repeats forever. So basically, this is just numbers mod 26. So if you ever get a number that's more than 26, just mod it. And for each character in the message, find the corresponding number, multiply the number with the corresponding digit, and then transform it back to the character. So basically, all you have to do is convert this into a number, multiply by corresponding digits, and then convert it back to the character. You're told that the key that you use to multiply is exactly the same as the length as the messages. So really, there's not too much to say. Um, you read the message, you read the multiplier, you read the message, and then I call this encode that takes the character in the message and the character in the key. So the key, um, yeah, the key, if you want to convert it to a character, from a character to a value, I just subtract it from the ASCII value of 0. That would be the numbers 0 to 9. And then I convert the character A to Z to 0 to 25, multiply them, um, and then mod 26. So that would make sure that you get back to 26, and then back to 0 to 25, and then you add A back to get the character. That's pretty much it. So I guess if you don't like it, I don't know why I have Amigos here. I don't use it anyway. Um, if you don't want to do a function, you can actually just write it in line. It's just one single formula, but it doesn't really matter. It's cleaner for me to think about, but it really doesn't matter. Okay, so second problem. Okay, so here you have a bunch of people, they all speak a language. You want to know, given an arrangement, so they gave you an arrangement like this, what is the minimum number of, okay, so the awkwardest level of a seating arrangement is the minimum number of seats separating any two guests speaking the same language. And if no people speak the same language, then the awkwardness level is defined to be n, which is the number of seat guests. 2 seats next to each other is said to be separated by 1. So for example here, 1, 2, 3, 1, the only thing that repeats is 1, and they're separated by 3 seats. And here, um, there's nothing that repeats. Okay, and the number of items can be up to 100,000, and each number can be anywhere between 0 and 10, 10 to the 9, which is a billion. All right. So basically, what you have, my writing tablet is not connected. Let me just connect it. Okay. Okay, so it's connected now. So you have a bunch of numbers, A0, A1, A2, up to AN minus 1. And I want to find any pairs or anything that's the same. If they're not the same, I don't care. But if they're the same, let's say this one and this one are the same, I want to know the distance. Now, it could be that the same thing occurs multiple times, but I really don't care about anything before that. I only need to know. In this case, I need to know the previous one, and in this case, I need to know the previous one. So if you just scan things this way, all you have to know is when you see something here, have I seen this before? If not, that I don't really care. But if I have seen this before, I want to know how far back was the last time. So basically, I need an array or some kind of data structure allows me to say, what is the position of the last time I've seen this, if I've seen this at all, right? Now I write it like this, but you really can't use an array because this value can be anywhere between 0 and 10 to 9, so you can't have an array that big. But what you can do is use a map, right? So you can use a map and say, have I seen this before? And if I have seen this before, then I can calculate the current position to the last one. And in any case, after I've done this, I remember the last position of whatever I see here as the position, right? And that's pretty much it. If you use a map, then access and then inserting its log n time. You can also choose to use an unordered map. In this case, it's good enough. You don't need an order. And unordered map, it's basically constant time, more or less. This is underneath is a hash table. So either one would work. So I'll just show you my code. It's fairly straightforward. So I use a map here. This is the last position. The key is the value, and the value of the map. So key is the value of the array element, and the value of the map is the position. Right. So my answer is at the beginning and, because if nobody repeats, then that's the answer that they told you. And I just keep reading. For each element, I ask right here if I have seen this before, right? So what you don't want to do is use last bracket X, because when you use last bracket X, if there's no entry, it will create one with the default value, which is 0. So before you actually do last bracket X, you want to call find to see if this is actually there. So last.find X, this will find it if it's there, and if it's not, it will not try to create an entry. So last.find X, it will create an iterator to point to the element, or the special iterator last.and if it's not found. So if it's not last.and that is found, then the difference between my current position and my last position is the distance, and I just take the minimum, or keep a running minimum. And in either case, whether I found it or not previously, I just remember that for this value, I is the position of the last time I see. Okay, so that's these two sort of warm-up questions. Okay, let's look at something a little bit more complicated. Okay, so you have a chemist, and you have a bunch of these chemical elements. There's a big table of it, right? And then you can only speak a word if it can be spelled as a bunch of chemical elements. Okay, all these chemical elements, they are at most 2 characters long, right? Given a word, determine whether the declarer can speak it. If it's a concatenation of atomic symbols, without your help, she might as well have taken silence vowels. You may identify upper and lowercase letters. So basically, upper and lowercase don't matter. They're all the same. And here's the complete periodic table. Input consists of up to 10,000 test cases. Each test case is a word that it's positive and does not exceed length 50,000. Total number of the length of all the words across all test cases is up to basically a million, right? So even though you have 10,000 cases and each word can be up to 50,000, it's not just that you can have a file that's 10,000 times 50,000, because that would be quite large. That would be like 500 megabytes. But anyway, they tell you that at most there are up to 1 million, more or less 1 million characters to deal with. Okay. And they also tell you that there's a 5 second. 5 seconds is actually pretty generous, but still, it doesn't mean that you can do whatever you want. Okay, so what are we going to do? Well, first, there's this big mess, right? There are all these characters, all these chemical names. You likely don't want to type this whole thing in yourself, right? Because you can probably screw up somewhere, it will be extremely difficult to debug. And then the second part is what is the algorithm? Okay, so let's start with the algorithm part. You have a string, okay, and you have all these symbols. I don't even carbon, oxygen, and whatever. Okay, there's a bunch of them. Gold, I think is AU, etc. Okay, but all these things, all these chemical names have length 1 or 2. Okay, so that's one thing that you can verify by looking at the chemical names. There's nothing more than length 3. So if something is length 1 or 2, maybe it's easy to check. Well, certainly if something is length 1, what do? You just ask, is it in the list, right? Because there's no other way you can break it up. But if something is length 2, then you have the possibility of breaking it up, or it could be one of these. So if it's length 2, you have to ask, is it part of this list? And if not, maybe I break it up into 2, and then maybe each letter can be written as. But what if you have a longer string? Well, if it's a longer string, then you can say the first one, let's say the last one, doesn't really matter whether you do it in the first part or the last part. You might say, well, maybe the last character is part of this. So maybe this is an H, so it's done. You can do H. And recursively, the first n minus 1 characters can be done. Or maybe the first letter, the last letter is not part of this. Maybe it's like an E, but the last 2 letters are that. And when you recurse, the previous n minus 2 characters can be done. So basically, if f of n is true or false, what is true if first n letters is yes. Okay, so I mean, what is yes? It means that you can concatenate a bunch of chemical names to form the first n letters. Then what do I know? F of 1, I just check if it's in the list. That's the easy part. So that's one of the base cases. And it turns out that it's also quite convenient to say what is the empty string. Empty string, you can always do it, right? Just by saying nothing, you can do it. Now f of 2 is a little bit harder because f of 2, you have 2 choices. You can either try for finding one of these, or you can try breaking it into 2 lists of the 2 substrings of length 1. But in general, if n it's greater than or equal to 0, actually, let's say greater than or equal to 2, then it's f of n minus 1 and last character is in the list, right? So if the last character is in the list and the first n minus 1 characters recursively can be written as a concatenation of chemical names, or f of n minus 2 and last 2 characters is in the list. Those are the 2 options. Okay, because the last, basically you're saying, well, I have to concatenate with a bunch of words, so there has to be a last chemical name. What can this chemical name be? Is either the last character or the last 2 characters. Maybe both are working, maybe both are true, but one of them have to be true. And if the last character is in the list and the first n minus 1 characters can be written as a concatenation of chemical names, that's good. Or the only other choice is if the last 2 characters is in the list and the first n minus 2 characters are can be recursively written as a concatenation. Okay, so this is basically dynamic programming. And why do I need f? N has to be at least 2, because if n is 1, then I can't use this, right? So alternatively, you can say, uh, you can do f of n like greater than or 2, but then f of minus 1, it's also true or something like that. Or f of minus 1 is false. So either way, doesn't really matter. So basically, this is a one-dimensional dynamic programming, and we've seen dynamic programming the last 2 weeks. So all you have to do is remember, right? When you compute f of n the first time, you remember it so that the next time you check, you have already computed it, so you don't have to compute it again. So n is up to 50,000, so that most 50,000 table entries that you have to compute. But in any case, it's sort of linear, right? Because, sorry, it does say that you cannot have too many long strings because the total size of the array is the total size of the input. It's up to 1,000,000 characters. Okay, but anyway, let's look at 50,000. Okay, but here, so basically you have two choices, right? You do this one or you do this one. So it's two choices. That's pretty quick, except that you have to check if the last characters in the list, the last characters, two characters are in the list. And the question is, can we do this quickly? If you can do this quickly, then you basically make it this computation of f of n linear time in n. Now, there are ways you can do this. You can store and organize this list of strings into a data structure that allow you to do everything in constant time. Okay, and if you want to look that up, it's something called a trie. And in fact, in this case, you might want to do a trie on reverse, um, the reverse of all the characters in all the chemical names. So instead of HE, you would store EH, and because I'm reading things backwards. But because trie is not a data structure that's easily available, you have to write it yourself. It might be better just to do something else. So we're going to use, for example, a map or a set, I guess. You can use a set because you don't need to keep a value, you just need to know if something is in there or not. So if you use a set of string underneath is a binary tree, that means it's log n comparisons. And now you have to be a little bit worried, perhaps, because first of all, comparison is not a straightforward comparison. These are string comparisons, but because the strings at most length 2, so I guess you can call it constant time. And then also it's log n and so on. If you want to make it constant time, but constant number of comparisons, well, actually, you don't use comparisons in hash tables. You can use unordered set, and then there's a hash function that's already defined for strings, and the hash function would have time proportional to the length of the string. In any case, what I want to say is whether you want to use a normal set or an unordered set, there's a hidden complexity factor, which is the length of the strings that you're putting in. But because in this case, the length of the strings are limited to at most 2, you might as well consider as constant. Okay, so that's basically the idea. But there's still a practical problem. Do I want to type this in myself? Right? There's a lot of stuff here. And actually, it doesn't even show. The window isn't wide enough somehow. And there's a scroll bar on the bottom. So if you have the opportunity to use this electronically as opposed to a printed statement, the answer is no, I do not want to type this. So what do? I can copy paste it, right? I can copy paste this. But of course, this is in a form that might be a little bit difficult to use. So how do we do this? So I want to show you how I deal with this. So let me just show you. I have this memo array. I know it's true or false, but I make it integer because -1, so a 0 and 1 would be true, and the 1 is true, 0 is false, and -1 would be uninitialized. So at the beginning, I fill it out to -1, and then I basically call this function. I call possible, yes or no, with the length. And then here, right, if it's n is 0, I return true. Then I look up the table entry. If it's greater than or equal to 0, that means I've already computed it. So it's true. Here, actually, I don't even count. I don't even care if it is 1 or 0, if the length is bigger than 2. So I just check if it is in my dictionary. Then I just say true. So I didn't even bother checking if the length is 2 or more. But anyway, so I just checked the whole word. And then here I ask, oh, actually, this is wrong. This is very wrong. Okay, just pretend that you didn't see this. Because I passed in the word, so I'm only checking the whole string every time. I never take a substring or anything. So it's not that it's wrong. It will give me the right answer, but it's completely useless. Anyway, why is it? Why does it? Why is it okay? Because it actually get caught by the other part uh, along with n equal to 0 as a base case. So if it is violated in this library, sorry, if it's in this word is actually in the dictionary, it will grab it as the last 2 characters, the last character here, and then when I recurse, it will reach the base case and give me true. So this part is actually completely useless. Anyway, hang on, let me just fix this. There's no point having this. Okay, let me actually just submit it and make sure that it actually will work. Actually, it's easier if I just look at my previous submission and get rid of this. How do I do this? Edit, resubmit. So that should save quite a bit of time because I'm not checking this every time. Oh yeah, you see my previous submission takes 2.19 seconds and now takes 0.04. Okay, anyway, so yeah, I was doing something unnecessary here. So why don't I bother with n minus being 1 or 2? Because here I say either, so I know that n is not 0, so n is at least 1. Either the last character is part of my dictionary. So this is one way. If I have a map or a set, I can say how many times does it occur. And if it's not, if it's a set, then it's either 1 or 0. And recursively, the first n minus 1 characters will work. Or this is the same, except that I add an extra condition that I only check this if n is greater than or equal to 2. So I basically replace all of that. And remember, I always set the answer before I return it. Okay, so what do I do with this? Right, so first thing is I copy and pasted this. And in C++, if you're multi-line strings, you can just put them together like this. A string followed by another string with no operators in between. That's guaranteed to be concatenated. Now, one thing though, I inserted a space at the end of each line. Why? Because if I don't, then when I concatenate, it's become HELI as one string. So I don't want that. Alternatively, if you want, you can have an array of strings and then just deal with it later. Okay, so I have another list of another set of strings called dictionary. And then what do I do? Right, so initialization, which I call right at the beginning, I transform all the characters to lowercase. So this is a way to turn all the characters to lowercase using a transform function and the to lower here. Actually, I'm not quite sure why I did the colon colon. Colon colon just means use the global one. Does this work? Oh yeah. Okay, so this is a little bit weird perhaps, and part of it is because I included every single thing. To lower, it has convert this blah blah blah. And here we have standard to lower. And then there's a different one. But this is in standard locale. So if you have multiple. To lower is one of these strange things that I guess this is something that we call historical reasons. So in the old days, if you just use to lower, it might not actually be a function. It might actually be written as something called macro that inlines the conversion, which is a simple calculation. And so if you just use the word to lower, it might not actually be a function. It might actually be some code that the compiler inlined. And it's possible that if you just do that, it will just inline. But if you use a colon colon, it forces it to not use the macro substitution. So just for fun, so what is minus E? Minus E stops at the preprocessor. So it doesn't actually compile, but it processes all the include and so on. Okay, hang on. That's too much. Okay, so it will include all the stuff that includes, right? So for example, there's here using colon, colon, blah, 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 and so on. Okay, all the things that you included, it's here. Okay, so let's actually go and read. So this is our code that we wrote, and then all the other stuff. Okay, now this is too lower, right? So that's no problem. But if we get rid of the colon colon, let me just write it to something else so I don't screw up my old file. This has to lower, and there's a function here called to lower. This underscore to lower using colon colon to lower. Probably it's because it doesn't know which to lower it is, because there are two versions now. So if I don't So candidate expects 5 arguments. Unresolved overloaded function because it probably doesn't know which one. Candidates are this. Failed the substitution. Blah, blah, blah. Maybe it expected another one because 2 lower might want more. I don't know exactly. Anyway, okay, it's not important. What was it called? Chemist vow 2. I will get rid of that. Okay, anyway, I just want to show you that it doesn't work if you don't do that. Okay, so what did I do? I just have this string, and then basically now that things are separated by spaces, I turn it into a string stream. So when I read the words, it will be separated. And then anything that has the stars and double star, I just don't bother inserting. It actually doesn't matter. You can insert them anyway. Why? Because in your strings you will never find them anyway, right? So because the strings only includes letters, so even if you insert these, it doesn't really matter. But just to make things more easy to understand, I just decided not to insert anything that starts with a star, and that's it, right? So there's of course the dynamic programming side, but also I want to show you sort of a way to avoid typing all of this stuff in yourself if you have the electronic version available. All right, next one. Palindrome substring. Palindrome is a word that reads backward, same backward and forwards. You have a string. You want to find a non-trivial substring of B that reads forwards and backwards. That means that it's at least 2 characters long. And you need to find all of them and sort them all lexicographically. It should not contain duplicates. Okay, so when you see the word should not contain duplicates sorted lexicographically, that one of the things you can do is just throw them in this set, right? If you can find them all, throw them into a set, then it all comes out automatically with duplicates removed, and you don't have to worry about sorting because that's just how it comes out. So that's kind of the first thing to realize. And how many palindromes can you have, right? So each line contains up a string of 1 to 1,000 characters, a lowercase only. So in the worst case, if every single character is the same, right, then every single substring it's a palindrome. But in that case, there'll be a lot. So there are n square substring because they're basically n choose to starting and ending point more or less, and everyone is a palindrome. But because you want uniqueness, right? You can't, even if they're all the same letters, right? Every single substring is a palindrome, but um, you can't have 1 million different substrings that are unique. Okay, but in any case, let's just say 1 million. At most 1 million, that's the absolute worst case. Throwing in a set is fine, okay? But it's actually much less usually. Okay, so how do we check for all palindromes? Substrings, right? So how many substrings are there? And you choose all possible start and end points. That's basically n choose 2 substrings. So that's already n2, n square, O of n choose 2, which is n square substrings. And if for each substring you check whether it's a palindrome or not, it could be another big O of n checks. So it'll be n cubed time. That's too much. So how do we do it better? right? How do you normally check for palindromes? Well, there are a number of different ways you can do it. One way you can do it is, let's just say this is a palindrome or not. Maybe you start from here to here, and then if they're the same, you keep going, and if they're not the same, well, you stop. You know that this is not a palindrome, right? As soon as you find a mismatch, you know this is not a palindrome. But the problem is, let's say this is A and B, right? Just because you know that this is not a palindrome doesn't mean that you don't have a palindrome inside. Okay, so what if we do something different? Instead of working outside in, let's work inside out. Let's say that for now, this is an even length palindrome. So the middle would be A and B. As soon as you see A and B, this is a mismatch, you know that there are no other palindromes, even if everything are the same. There cannot be any other palindrome center around AB. On the other hand, if they're AA, then you keep checking. So if you want to know how many palindromes are centered around AA, let's say, you can do it in linear time because at most you have to scan this way and that way the whole string. Sometimes a lot less. For example, if you're over here, right, you can't scan too far because you get the edge already. So basically, you check every possible centers. There are n centers, roughly, because it depends if you're looking at doubles, right? Then there are actually n minus one centers. And then when you move out to check, there's at most n checks. So this is n squared, which is good enough for n is 1,000. Okay, but what about these are all the even length palindrome. What about the odd ones? Well, it's the same thing except that your center is length 1. So you try all the centers of length 1 and move out. And that's what you have to do to get it done in time. So I have a set of strings. This is my answers. N is the length. Then for each one, for each center, the odd length palindromes, basically I'd say I check all the positions, and J, it's how far I have to go. J1 means I look both sides one step away, 2 is 2 steps away, and so on. And the two that I look at would be this one and this one. So you can do some arithmetic to figure out. Sorry, it's the two that I look at are I minus j and I plus j. As long as these two indices are in bounds and they're the same, I keep going. And when I keep going, I insert the appropriate string. So you have to do some index calculation to figure out where the substring is that is palindrome. And then the even length, it's similar, but I have to be a little bit careful about the indices. So it turns out that the only change is I have to change this index to be +1. And then at the end, I just print them all. Okay, so that's pretty much it. So I guess the thing is to realize that you can check palindromes by looking at the center, right? And then you just spread out, and that's how you can get n square time instead of n cubed time. You don't have to check every possible pairs of start and end points. And you can just check the centers and spread out. So you can redo, basically you can redo the work, right? When you're checking palindromes, if you're doing inside out, then you don't have to keep checking the whole thing because you know that as you're doing things inside out, things that you already checked in the previous step is already a palindrome. You're just adding one character before and after. Okay, the last one is the most interesting one, perhaps. Automatic trading. So basically, you have a long string up to 100,000. They will have uppercase and lowercase a to z. And basically, you're looking for the longest sequence of identical strings. So the longest substring. Oh, sorry, longest sequence whose starting points are the first thing. So here's a string, but I'm going to ask this multiple times. So here's a string, and I have three queries. 0, 2. What does that mean? 0 and 2, those are the two positions. And from that point on, the longest wait, why is it 4? Okay, hang on. Let me see. Okay, so here's a string. Oh yeah, 0 and 2. And from this 0 and 2, AB, AB, and AB, AB are common. So the answer is 4. 1 and 6. 1 is here. 6 is here. So there's nothing in common. So the answer is 0. 0 and 7. 0 is here. 7 is here. And ABABA is the longest common substring. So I'm asking for longest common substring starting at certain positions, but I'm also asking many, many queries, right? So if there's only one query, the answer is pretty simple. I just start from 0, I start from 7, I just keep reading until it mismatch. The worst that can happen is linear time, the length of the string. So if there's only one queries, I can do it in linear time. The problem is I do a lot of queries. I cannot afford to do linear time per query. So here's another one. She sells seashells by the seashore. And then at position 8 and position 22, 0, 1, 2, 3, 4, 5, 6, 7, 8 is C. And I guess 22 must be C as well. All right. How do we attack this problem? The fact that you have one single string with multiple queries means that you can afford to pre-process the string somehow. And the question is, what kind of pre-processing can we do to make our life easier? So from last week, we talked about suffix arrays. So suffix arrays, let's say, okay, the favorite string is banana, right? So the suffixes that starts with these positions are 0 is banana, 1 is anana, 2 is nana, 3 is ana, 4 is na, na, and 5 is just a. And then suffix arrays sorted alphabetically or lexicographically into this. And the suffix array would be 5, 3, 1, 4, 2, 0. And we also said that there's something called the LCP, which it's the longest common prefix, right, between and prefix in the suffix array and the previous one. So this 1, 3, 0, 2, 0, like this. Okay, so why is that useful? Because things that appears together, right, A and A, repeated substrings are appearing together in this suffix array. All right, so let's say that I asked you, what is 1 and 3? if the query is 1 and 3? Well, the answer is A and A because that's the longest substring. And how would I know that? I look at this suffix array, 1 and 3, and they happen to be together, so 3 is the LCP. So that's the answer. That's the longest substring that overlaps. Okay, maybe it's not so. Maybe 1 and 4. Okay, let's not do 1 and 4. Let's say do 3 and 4. Okay, 3 and 4. You might say, well, that's just next to each other. It's clearly 0, but maybe we don't know that. So 3 and 4, we look up where 3 and 4 are in the suffix array here. And I look at the LCP entry here. Now, why do I not include this one? Because this is the LCP between this one and the previous one, which is out of the range. The range, it's here, and these two entries are the ones that covers the LCP of these things. And the minimum of these values, it's what I need, which is 0. Okay. If I were to say, well, what is 1 and 5? Well, I look at 1 and 5. So let's undo all of these things. 1 and 5, the longest overlap is A. How do I find out 1 and 5 in my suffix array? I look at the LCP values, take the minimum, it's 1. So what is going on? If I build the suffix array of this string, compute the LCP, and if I know quickly, given a position, where is it in the suffix array, I can easily ask whatever range it might be, I need to know the minimum of a certain range in my LCP array. So if you have been listening to the past few weeks, basically my algorithm is this. Step 1, compute suffix array. And LCP. 2, find a mapping from position in original string to position in suffix array. How do I know that? How do I do that? This is guaranteed to be a permutation of 0 to n minus 1. So if I just scan through this, so this, I don't know what I call it. Let's call this mapping. Let's call it index. If I just do a loop on the SA value, then when I see 5, right? So if I say SA of I, it's equal to I. So for example, index of 5 is equal to 0. Index of 3 is equal to 1. Index of 1 is equal to 2, and so on. So if somebody asks me, what is position 1 and 5? Well, I just go and look it up. 1 will be 2, 5 would be 0. Now, of course, because this is scrambled, I need, oh, okay, hang on, I'm jumping steps here. 3, build a range minimum query structure. Okay, so we talked about this before, and then you just repeatedly ask the right range. So what is the right range? If they give you position 1 and position 2, let me find some space. So the right range, if they give you position 1 and position 2 in the original string, then I would take the map that I built into the suffix array. So call it, I don't know, A1 and A2, let's call it. And now one thing to remember is that A1, it's even though position 1 might be less than position 2, there's no guarantee that A1 is less than A2 because it's all scrambled now. So the start of the range, it's actually the minimum of A1 and A2 plus 1 because we need to, in the LCP, start 1 later in this range. And the n is max. And we just use the minimum, a range minimum query structure to keep doing this. So you chain the code for suffix array, you chain the code for range minimum queries, and that's what you can do. So this is called automatic trading. So first I paste the code for suffix arrays. So this is just a code for suffix arrays. Then the code for construct RMQ. This is actually range maximum because that's what the code does. But we negated it so maximum becomes minimum. Anyhow, you build a suffix array. This is this mapping that we did. Compute the index, compute the LCP, construct the range maximum query, but maximum of the negative numbers is minimum. And then basically this is what I'm telling you. It's the maximum of the minimum of the indices plus 1. So the minimum of the indices plus 1 and the maximum of the 2 indices, and then I have to negate it because it was I negated everything at the beginning. Okay, so that's the code. Oh yeah, there's a reason why. This is funny thing about the star, which is not in the problem statement. There's nothing about stars, but in a very, very original problem that was originally used, the problem had it so that it's not a single test case and you quit the program when there's a star, basically. Where is this problem from? 2013 University of Chicago Invitational Programming Contest. This was actually what used to be called what the predecessor of the North American Championship. So this is definitely a problem that's a little bit at a higher level. But I want to show you a completely different way of doing this. Okay, so this is a lot of code to type and all that stuff. So let's think about a completely different way of doing it. I have two position 1 and position 2. I want to know what is the longest substring that are equal. First of all, if you know, right? So if you have a quick way to say if the length is k, if you think the length is k, can you easily say yes or no? Length k, are they the same? Are they not the same? Okay. If you can do that, you can turn this into binary search. Why? Because if these two positions have at least k characters in common, then any number smaller is also a yes. Right? So we have this structure, the length that you're guessing as the longest length that they have in common. 0 is a yes, always. And then at some big number, the answer is no. And if the answer is yes for 1 and 2 and 3 and 4, right? If the answer is yes for 4, it's always the same. The answer is also yes for 3. So you basically have a bunch of yeses. And then once you get to a no answer, it will always be forever no. And that means you can use binary search, right? You know it's 0 is a yes, or I guess you can check if 1 is a yes. That's an easy check. You know that anything that's bigger than the length of the string is no. And then you're looking for this point. So what do? You take a step in the middle. If it's a no, you move the high pointer to down. If it's a yes, you move the low pointer up. And then at the end, if you always make sure that low is a yes and high is a no, then the answer is where the low is. So we're going to do a binary search. The question is, how do you do a binary search to quickly, and I mean quickly, decide if these two substrings of length k are in fact the same? All right. So last time we talked about this idea of hashing. So we turn these letters, in this case, you can use 256 because 52 because you have uppercase, lowercase, there are 52 characters. You can't just use 26, or you can just use 256 and then not worry about anything else, and then use a prime. Okay, so we'll kind of ignore the fact that you're using prime. We'll just, we want to be able to say, what is the hash value here, right? So you have some characters, C1, C2, up to CK, right? And what is the hash value? So what is the hash value? There are many ways, so it depends on which way you do this, but maybe you say this is C1 plus C2 times, let's say 256, plus C3 times 256 squared, CK times 256K minus 1, and then mod some prime. Okay, we'll not worry about this for now. Okay, so how can we easily do this? Here's the trick, right? If you have to compute this every single time, you're lost. You can't do this. It's too slow. But whenever you're looking for a sum, a contiguous thing, here's one way you can do this. You will compute originally, so just in advance before you even start, the value of C1, so your original string S, S1, S2, S3, this is your whole original string. Let's convert it to numbers as 0 to 255 if you want. And then you can say, okay, let's look at S1, S2 times 256, S3 times 256 squared, S4 times 256 cubed, and so on, Sn minus 1 to 256 n minus 2. Now, these are very big numbers, but of course, we're doing this mod p, so it doesn't matter. So let's say you computed an array like this. And now we do partial sum. So this is, I don't know what we call it. We call it partial sum. What does partial sum do? It adds up everything from the beginning of the array of values. So this is S1. This is S1 plus S2, 256. This is S1 plus S2, 256 squared plus S3, 256 cubed, and so on. Okay, now why is that helpful? If we want something in the middle here, what we can do is we can take the partial sum of this chunk, right, whatever this chunk is, minus the partial sum of the chunk before it, right? So let's say you want the partial sum starting at S4. Okay, so S4, S5, S6, and whatever. I guess this is maybe K plus 4. So this would be K minus 3, like this. Okay, oh, sorry, plus 3. Well, you compute a partial sum up to this point, and you have S4 256 cubed plus S5 256 4 plus dot 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 C plus K plus 4 256. Oh, this should be sorry, this should be just K. Should just k, k minus 1. Okay, hang on. I got the indices wrong. This should be k plus 3. If I want k of them, and this would be k minus 1. Okay, this is more like it. So the partial sum of up to this point would be S1 plus S1 plus S2 256 plus S cubed S3 256 squared. Hang on, this is all wrong. Okay, plus this much, all this other stuff. So if you take the partial sum of up to here minus the partial sum of what's before, you'll get exactly this much. So in 2 lookup of this partial sum table and 1 subtraction, you would be able to extract this much. But you'll see that compared to what you want as a hash value, you're off by a factor of 256 cubed. So what do? You divide by 256 cubed. So basically what you have to do is if you wanted the hash value of a chunk, you take the partial sums at this value minus the partial sum of whatever is just before, and then divide by the correct power of 256. And the correct power, it's based on where you start, right? If you start at position 4, you divide it by 256 cubed. And that's it. Now, of course, dividing mod p requires something special. But if you know what that means, right? If you want to divide by 256 inverse mod p, that means I'm looking for the solution of the inverse like this, right? So if I want to divide by 256 or multiply 256 inverse, it's the same thing as multiplied by x, where x satisfies this equation. And there's something called the extended Euclidean algorithm, which is in the code library, which allows you to compute the GCD of 256 and p. And because p is prime, you know that the answer should be 1. But the extended Euclidean algorithm will also find two numbers, s and t, such that this is true. The two things that you put into a GCD calculation and the GCD, it's always related by a linear combination with integers. Why is that useful? Because when you take things mod p, 1 is still 1. This is a multiple of p, so that disappears. And this s, mod p, is your inverse. And if you pre-computed s, all the powers of s to 0, s to 1, s to 2, all the way up to s to the n minus 1, then you can just look that up when you have to divide by the inverse, divide by power of 256. So this is the other version. So forget about the hash 1, hash 2, just do hash 1 for now. So this is a prime. It's a relatively big prime. It's not the biggest prime. And I pre-computed what is space. Everything is 256. Oh, I use 52. Okay, it doesn't actually matter, I guess. So I just use, instead of 256, I use 52. So I basically map each character between A to Z, uppercase and lowercase, to 0 to 52. And then inverse of this. And then this is the basically 52 inverse mod p. And now I'm using two primes here, but let's just do 1 prime for now. So what does solve do? Solve computes the hash values Okay, so this is the hash values of each character multiplied by the base. And then every time I go to the next base, the next position, I increase the power by 1, right? Multiplied by another 52. And then this is a partial sum. Uh, so I have to do the partial sum, but I have to make sure I use mod. And then the longest common prefix of position A and B, what do? I basically do what I said, which is I check if they're not the same character, then I know the answer is 0. Otherwise, low is a yes, high is a no. And I take a step in the middle, and then I just check if the two hashes are the same here. So here I compute the hashes. This is the hash of the A and hash of the B, and then I multiply by the inverse. Okay, that basically is the power of the inverse. Where do I do that? Oh yeah, here. This is so yeah, I said that compute by extended Euclidean algorithm instead of hard coding it in. I guess I work it up by hand. Um, Now, why do I use two hashes? So one thing about hash is that you can have collisions. And collisions, if you have two substrings that are actually different but have the same hash, that's bad. By using two different hashes, the chance of collision is much less likely. So I just use two. So let's see if, let me get out the contest and look at the general. I don't remember if there's a hash version. If I use only one, whether that would be good enough. So let's just try it. So let's not bother with hash 2. We just pretend that that didn't exist. So we still computed it, I guess, but I'll just not check it. So it is pretty unlikely, but it's possible. When you use two primes, so this is basically 1 million chance, right? But when you use two primes, you kind of this size, you basically make it to 10 to the, instead of 10 to the 6, it's 10 to the 12. So that's, I guess, one thing that you have to be careful. Now, this was done a long time ago, 2013. I actually did this problem in 2013, actually. I guess it doesn't say that, but I'm actually the author of the problem. Um, and since then, in 64-bit integers and so on are more readily available. So you might want to use bigger primes and use 64-bit integers instead. And maybe that would be good enough. I haven't checked that. So anyhow, there's two different ways you can solve this problem. You can use it a hash and with binary search, or you can use the suffix array approach. So in any case, I just want to show you both of these. All right, so I guess I'll stop now.